looking to find the domain, what you care about is what the non-permissible values are, what the restrictions would be. So what you would do is just factor the bottom. Now you could also factor the top right away, so let's just go ahead and do it. So it's going to be x minus 3. What are the other factors up there? X plus 1? Plus 1 and plus 2? Okay. So it factors to that. Now the bottom is just easy factoring minus 3 and plus 3. Now anything on the bottom is going to give us a restriction. Okay? Any factor on the bottom will give us a restriction. So this means our restrictions here are going to be plus 3 and minus 3. So x cannot be plus or minus 3. Now to write that, formally as a domain, if we're using interval notation, we would say it goes from negative infinity to negative 3, from negative 3 to 3, and from 3 to positive infinity. Okay, because there's 3 distinct pieces to that graph. Okay? There's 2 different places where we have a discontinuity. So we have an infinite discontinuity at negative 3. That's because it's approaching infinity on either side, Aiden and Sebastian. Okay, and then at positive 3, there's a hole there. Okay? There's just like a tiny hole. You can't actually visibly see it on the graph, but it's there. Okay, so it's just knowing that that hole is there. Okay, so this graph, the rest of the questions are asking you to look at the way that graph looks. Does someone have it open on their calculator? Is it like this? Yeah. My God, my stylus is driving me nuts today. This app had like an update, and it seems like the worst update of all time. Okay, it's something kind of like this. Okay, it's okay if it's not exactly like that. But the point of it is that there is a hole at 3. So there is a hole in our graph at 3. And what they're asking us to do in the rest of the question is to figure out what I could put in there to fill that hole. Okay, so you want to fill it at exactly the right spot so that you could trace that part of the graph without having to lift your pencil. Okay, so the way we would fill that hole and the way we'd figure out how to fill that hole is by removing the removable discontinuity. And we actually literally do it. So as we look at the limit of x approaches 3 of this original function, I look at the factored form and I realize, hopefully, that I have a common factor that I can remove. Okay? And when we remove that common factor, we're also removing that point of discontinuity. So then we can plug 3 into what's left, and if we do that, we get 10/3. Okay? So what that means is that this point that I want to fill in, the coordinates for that point are 3 and 10/3. That's what it means. Okay? Is that coordinate that fills that hole is at that exact precise location. Okay? So now if I'm tracing that piece of the graph, okay, it's continuous. Okay? Because I have the hole filled in. So the way we can write that the hole has been filled in is using that piecewise function notation. So we say it's going to still be the original function, x cubed minus 7x minus 6 over x squared minus 9, at everywhere except at x equals 3. Okay, that's what x cannot equal 3 means. It means it's going to be like that everywhere except at x equals 3. And then at 3, we say it's 10/3. So we're saying we'll just fill in that one point on the graph at 10/3. And now we've created anything above -3 here, it's continuous now, okay, for the rest of that domain. It's still not continuous at the infinite discontinuity. Okay? Okay, so that is kind of what they're getting at here. So this is how you would fill a point of discontinuity. This actually does come up in Math 30-1 as well, when you do rational functions. You learn about points of discontinuity and about how to find the y value. This is the same concept. It's how you find the y value of a point of discontinuity. Okay? So the y value here is. Okay, now this definition of continuity is in the books. I don't know. I kind of feel like I should take it out of my slideshow, but it's in the book, and so I feel like we need to talk about it. But it's also ridiculous, so I don't know if I buy into this at all. And we'll just see if anyone can kind of see why. I had a student it was Kyle McKee a couple years ago, was like, wait a minute. And we talked about it a lot, and we realized that it doesn't make any sense. So, but it is word for word in the book. A continuous function is continuous on an interval if and only if it is continuous at every point on that interval. That makes sense. A continuous function is one that is continuous at every point of its domain. Sure, then anything's continuous, because it only has to be continuous on its domain. So, and then it actually goes on in the book to say, for instance, y equals 1 over x apparently is continuous. It's just not continuous at that one place, because 1 over x looks like this. Okay, so it's not continuous at 0. But it's still a continuous function because it's continuous everywhere in its domain. 0 just isn't in its domain. That's what it says in the book. That is not, I would go ahead and say that is not the general understanding of continuity. But that's what your book says. So I won't ask you any trick questions like that. But just so you know, like it says that in your book. It says that 1 over x is a continuous function. I would say 1 over x is not a continuous function. It has a discontinuity at 0. Okay, so I disagree with the book there, and this I think is just nonsense. But we should talk about it, just in case you were reading your book. I know some of you do that, or at home studying it up. So your book has some information in it that I actually Googled it, and it kind of seems like this is the definition that's used like by certain people at certain times, but I think generally speaking, like in a calculus class, that is not the understanding. Okay, so just so you know, it's really ridiculous. Yeah, because it says a continuous function need not be continuous on every interval. It's like, I think it does. You can say, like, you could say 1 over x is continuous from negative infinity to 0. I think you could say that, like, it's continuous on that interval. But I don't think you could say it's a continuous function. Okay, so properties of continuous functions is basically that if f and g are continuous, then f plus g is going to be continuous, f minus g is going to be continuous, f times g is going to be continuous. If you multiply it by a constant, it's going to be continuous. And f over g is continuous if g of c is never equal to 0. Okay, so that's, you get those discontinuities when the denominator is equal to 0. Okay, so there's just some very simple rules. Now, composite functions, let's do a couple examples here, quick ones. So if f of x is sine x, and g of x is x squared, what's f of g of x? Sine x squared. Perfect. Okay, and if f is absolute value and g is cosine x, f of g is cosine x. Okay, and the general rule is that if a function is continuous at x equals c, and g is continuous at x equals c, then g of f is continuous at x equals c. So it's just like kind of the same thing. We're going to see that. So like sine x is continuous, x squared is continuous, so sine x squared is going to be continuous. Okay, that's what we can say. Okay, absolute value of x is continuous, so cos x will be continuous, so the absolute value of cosine x will be continuous. And we can check it by graphing them. But like if you looked at something like, to me, if I looked at just the absolute value of cosine x, I have no idea what that looks like no clue at all. And I'm pretty good at imagining most graphs in my head. And I'm like, nope. Actually, I guess it would be pretty simple. Because now that I'm thinking about it, because cosine, right? Cosine is just, is like this, right? And absolute value, all it is bumps it up. So it's just going to be like all bumped up. So it's going to be like a bumpy, like that on the top. So I guess I can picture it. But if you couldn't, like if you were like, man, I don't know what that looks like. But if you know that these two are continuous, then you know that that last one has to be continuous also. Okay? So that's just a little trick. And finally, let's just show that this value is continuous. Because generally speaking, the continuity questions, I would say this is like the most common type of continuity problem, is you're given some kind of absolute value function, and you are asked to prove that it's continuous. This one would be like I'm going to go ahead and say a hard one. It's like a pretty difficult one. So what we would need to do is first figure out where this thing changes, because absolute values all the time, right? There's two halves to them. What would be the two halves of my absolute value function? What do I get when I have an absolute value function? I break it into two halves. What are the two halves I break it into? Positive and a negative. So I'm going to have a positive version of this, which is x sine x over x squared plus 2. And then I will also have a negative version of it, which would be negative x sine x over x squared plus 2. Okay, and I have these two different versions of it. And what I really need to do is figure out where they cross over. Okay, and where they meet. So if we graph it, try graphing it. Maybe even try graphing the absolute value part. So graph it looking at the absolute value of x sine x over x squared plus 2. And maybe put it into trig in terms of the zoom, because otherwise you're not going to be able to see much of it. Even with trig, it doesn't really look that great. Change your y, press zoom 7, and then change your y values to -1 and 1. Okay, so then you can see there's like a bunch of bumps there. Okay. 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 So we can see what it looks like there. I can see that it's definitely continuous. Okay. I'm actually going to erase this here because I think we should be looking at it differently. Okay. So what I can see there is it's definitely continuous. It's got like these bumps, right? Sort of like the one I drew before. It's like this random bumpity bump thing. Okay. But it definitely looks continuous. Now, one way that we can prove it's continuous, most of the time, I'll show you a different one, because most of the time they're not like this. But here what we can do is we can look at it, we can look at this as a product and quotient of functions. So for instance, if I call, and stick with me here because it's a little bit complicated, but if I call f just the function x, if I call g sine x, if I call h x squared plus 2, and I will have a function, I don't know, I seems weird, but I guess I should keep up my thing. I is the absolute value of x. Okay? I have 4 different functions here that I created for fun. Okay? So if I'm looking at y is just a combination of these functions. So let's just do what's inside the absolute value signs first. If I'm talking about x sine x, ooh, whoops. Oh my god. Okay. If I'm talking about x sine x, oh god, stupid. Okay. Seriously. X sine x over x squared plus 2. On top, what two functions are those? F and g. So that's just f times g. And on the bottom, that's h, right? Okay. Now, how is I related to all that? If I'm talking about my function y there, it's all inside I. So that's I of f of times g over h, like that. That's what this function is, right? It's a composite of the product of the quotient of this graph. Now, all these graphs, all 4 of them, are graphs I know. Okay, or I know anyway, and some of you might not know sine x, but I've talked about it before. Sine x is just a wave, a continuous wave for sure. But all of these graphs, I can confidently say, are continuous. And h, something special about h, because that's a division, and divisions can cause problems sometimes, right? Because divisions have discontinuities at zeros, okay, at non-permissible values. But there's something special about x squared plus 2. Nope. x squared plus 2. What's special about it that would make this never have any discontinuities? So if you square a number, what's it always going to be? It's always going to be positive. X squared plus 2 will never be 0. Okay? And that's actually really important in calculus. That comes up a lot where there's something like this. Will never. And that's important because that means that this will have no non-permissible values. Like there will be no values here where we're going to have discontinuities because H is never 0. Okay, we're never ever going to have a non-permissible. Okay, so my reasoning here for why this would be continuous is because since my stylus hates me. Since F, G, H, and I are all continuous, Y must be also, okay, by those properties that we learned on the page before. Okay, so that's a tough question. I wouldn't really expect you to be able to do that on your own, to be honest. I wouldn't think that was a fair test question. I would maybe put it on an assignment. Okay, but it's not that bad. I figured it out just now. Okay, I did it, so no problem, right? So if we have something like, more typically what you end up with is you end up with something like this. This is a question that you'll definitely be asked on the test. Maybe not this exact question. Maybe it is this exact question. I'm not sure. But you'll be asked something like this, and you'll be asked, prove Y is continuous at X equals 3. Okay, and it'll give you a point. Okay, now if you're proving, oh, we haven't actually learned the definition yet. Have we? No, we haven't. I'm going to leave this for next time. This is the more typically the kind of question you're going to be given. We're going to learn the official big, oh, maybe we did learn it. Did we? Did I learn it yesterday, the actual definition? We did, right? That the limit, yeah, we totally did learn it. I'm going to show it. Okay, so I'm sorry, this is a roller coaster. Okay, we learned yesterday that the limit, that something is continuous if the limit as x approaches a of f of x is equal to f of a. Okay, that was on one of the slides we looked at yesterday. Okay, that's the actual definition of continuity. So if you're asked this question, this would be a really typical kind of question to be asked. If you're asked this kind of question, what you're supposed to show is that the limit of this graph of x minus 3, the absolute value of x minus 3, is equal on both the left and the right, and that means the limit exists, and then the limit is equal to the function. That's what we're supposed to show. Okay, so what you're supposed to do in this question, if you're asked it on a written response, you're supposed to say, well, y is equal to, like Alex said before, we have the positive and the negative, and that's for when x is greater than 3, and this is for when x is less than 3. Okay, and that's how this works. That's how absolute value functions work. Okay, because 3 would be a 0. And then you take the left and the right limit of this. So the left limit of this, as 3 comes from 3 on the left, I would look at this function, because that's on the left, like we saw yesterday. So I just fill 3 into that. So it'd be negative 3 minus 3, it's 0. Okay? Limit as x approaches 3 from the right. From the right means greater than, so I'd look at this function, x minus 3. So it's 3 minus 3, which is 0. Now, since these are the same, I can say that the limit of x approaches 3 of the absolute value of x minus 3 is 0. Because on the left and the right, it's the same. Okay, I'm allowed to say that. Okay, now the actual function, x minus 3, if I plug 3 into it, is 0. So here, since the limit, since and I know that this seems like a lot of writing for it, but since the limit of x approaches 3 of f of x is equal to f of 3, we can say f of x is continuous. Oops. Is continuous at x equals 3. Okay, that's the actual definition of continuity that we learned yesterday. So you should use that actual definition in your answer. I know it seems like a lot of work. What I see instead, you're not going to be asked this all the time. You'd be asked it like one time. Okay, so you need to show all the work. You need to show that the left limit and the right limit are the same. So you have this function with a limit, and the limit is equal to the actual function, and blah, blah, blah. What I see instead is people go... they're like, yeah, I plug it in. What I see is usually, this is a good, actually not a bad answer, but it's not a terrible answer. What I see is students do this. They're like, okay, so I have x minus 3, and I have negative x minus 3. And if I plug 3 in, I get 0. And if I plug 3 in, I get 0. And then they write, I wouldn't lift my pencil. So it's continuous. And they're like, I'm done. Okay. Yeah. I mean, it's not terrible. And like technically, like they're correct. If it was a multiple choice question, this would be enough to get your answer. But in a written response, you need to be more what we in math call rigorous, which means use the actual definition given to you. Okay, not using informal understandings. Okay, so please avoid that. Okay.